right, so let's go through through another very nicely done library that's in Scala that can be useful and maybe not quite as useful as the XML, but still there have been situations when I've been able to put it to good use. And it's also, like as you'll see, a poster child for how you can make some pretty amazing syntax right inside Scala that's useful and intuitive. So this has to do with with parsing. So you get some file in some format that's not XML, but something that's custom. Later we'll have as an example JSON, but it often happens that it might be some other crazy format that's out there, and you need to, for whatever reason, you need to read it in, you need to parse it, and so you need to write a quick parser. Now, it used to be in the good old days that people had to take a course in compiler construction, and they would learn how to do parsing. Evil people have apparently removed this course from the curriculum, and so I'm not going to assume that you've ever taken a course, so I'll just give you a very, very fast introduction on how one specifies a language. So you have grammar rules. So here we're going to be using a very simple language in this example that just gives us arithmetic expressions. So when you want to have arithmetic expressions, you use rules such as the one over here where we say that a term is a factor times a term, where we'll see later what a term and a factor is. Or we can say a term could also be just a factor. And so these are rules where on the left-hand side you say you have what's called a non-terminal symbol, just a symbol in the grammar. In the English grammar, you might think of subject or verb or object, and in these grammars you have similar terms. Then you say, well, if if I have a term, then that's the same thing as then I could change it to saying I have a factor times a term. And then one can have these derivations of this grammar. So one can say that a term can resolve in a factor times a term, and then this term here can again become a factor times a term, and this term can become a factor by this grammar rule. So a term could be a factor times a factor times a factor. And then we would have another rule that says a factor could be a number, and then we could say that 3 times 4 times 5 would be a derivation in this grammar. And so one writes these grammars, and then out of that one can generate programs that will take input such as 3 times 4 times 5 and will say, oh, this is a term. And then you'll get a tree out of there that you can use to, say, turn that into code or evaluate the result or something like that. And so typically when you have a course in compiler construction, you will learn how to operate such a program that turns a grammar into a parser. These are called parser generators. And they generate generally very good parsers, but they're not necessarily easy to use. Whereas in Scala, as you'll see, it really is quite easy. So what a parser does is it takes input and turns it into some kind of, it just can do any number of things, but normally what it does is it turns it into some kind of tree that shows the structure of the input so that you can do something with it, such as generate code when you write a compiler. So we'll just do this in Scala, and you'll see just how simple this really is. So here's genuine Scala code to build a parser. So I'll walk you through this code and explain what each of these things are. So we're going to parse a very simple language which just does arithmetic expressions. We extend a class called Java token parsers, and we do that because this thing knows how to parse simple things such as a whole number that just parses an integer. And now we're saying an expression is something that is a term, whatever term may be, that's optionally followed by a plus or a minus and another expression. A term, and I'll give you an example in just a minute. A term is a factor, whatever that may be, which is optionally followed by either a star or a slash and another term. And a factor is either a whole number or it is a parenthesis enclosing an expression. So if you have something such as 3 minus 4 times 5. And now we want to know, is this an expression? And if so, how is it made up out of terms and factors? Then this parser here will give us an answer. What it will do is it will, first of all, so we're going to ask, is it an expression? So it's going to go into the first rule, and it's going to try to find a term, because it has to start out with a term. The term is going to try to find a factor, because that has to be at the beginning. The factor now says, okay, there's two kinds of factors. There's whole numbers, and there's stuff inside parentheses. It's going to look at the first token over here and says, well, this does not look like a whole number. But luckily enough, it does look like a parenthesis, and so we have a rule for that. It's going to consume the parenthesis. It's then going to go inside here, and through the miracle of recursion, going to map that against an expression. It's then going to, and I'm not going to go into that step right now, it's then going to find this closing parenthesis, which you have here, and it's going to say, hoo, I have found a factor. Now, that means that we're going to be popping out of here, and now comes this part where it says, optionally, is there a star or a slash? And sure enough, there is. And now it's going to try to match this against a term. And is that a term? What the heck was a term? A term was, it starts out with a factor. So it's going to try to call this function to see if it's a factor, and it's a whole number. So it's all going to work out. So when one draws a parse tree, this thing here was a whole number, which I'm not going to write down. I'm just going to write factor. And that was a term. And so all of these three things together here then formed another term, which was an expression. And so I didn't break down the stuff inside here, but I could do that in the same way. And then you get a tree that shows how this thing is built up out of a term, stuff on the left, the multiplication, and then the 5 on the right. And this thing gets further broken down, which I'm not showing, as the minus with stuff on the left and stuff on the right. And that then enables us to evaluate this expression. So the job of a parser is to take this input and to turn it into something that can be analyzed. Now, when you look at what happens in Scala here, you'll notice that there is a bunch of odd-looking stuff. There's these squiggles. And so we intuitively use the squiggles to say, first this and then that. So we want a term followed by an opt. Of course, a squiggle is something. It's an operator that whoever defined this library has defined what squiggle means. And what does squiggle have to do? If you look at on the left of squiggle, you see a function. And so squiggle will will combine functions into, as you'll see later, into squiggles, into these combinations of these functions. But as a user of this library, you don't have to care how it works. It just works. When you have something like whole number, this is something that eats up a part of the input, if it is a whole number, in fact, and otherwise it fails. When you have something like this gets turned into, by the stuff that surrounds it, into something that eats up a parenthesis if there is one, and otherwise it fails. The vertical bar it takes a parser on the left and a parser on the right, and it tries the thing on the left first, and if that doesn't work, it tries the thing on the right. Then we have these constructs opt and rep. Opt stands for optional. So opt says, well, I'm going to see if the stuff in here matches, and if so, then I'm going to return that, and otherwise I'm just going to return none and fail. We haven't seen rep in this example, but we're going to be seeing it later. It will try to repeatedly match something. So right now these things here give you a parser of any, and you'll see in a minute why that is so. These are functions, so I had to give a return type because they're recursive functions. Right? X calls term calls factor calls X, so there's a recursive chain. And so there's no type inference for such a recursive chain. In Scala, I had to say what the return type is. So these are all functions with no parameters, because what they do is they act on the input. They will consume the input, so there's this hidden side effect that the input gets less and less. And what they return is, as you'll see later, is up to us. Right now they're going to be returning an any. So the rules for these are that a string returns itself. So when you have a parser, that this thing gets turned into a parser, and that thing will return itself. An opt will return either sum of what's inside or none as an option. A rep returns a list of whatever is inside. The squiggle will return an instance of the class squiggle. So there actually is a class called squiggle. And it's kind of the same as a pair, but it looks nicer. The reason they didn't use pairs is because you're going to get squiggles of squiggles, and they kind of look linear, and it's intuitive in the order in which they were matched. Whereas the pairs, you have one pair sitting inside another pair, and it looks ugly. They could have used an arrow, and I don't actually know why they didn't. Yeah, but it's the same thing. Oh, yeah. So I don't remember. There was some reason why one couldn't use it, but so you can think of a squiggle as just being like the arrow, or not. It's just there. Okay, where am I? Yeah. So when we run this parser on this particular input, 3 minus 4 times 5, so we're telling, we're making a new instance of this thing. We're then telling it to parse. The parse method is inherited from the superclass from the Java token parsers, which is inherited from a more general parsing mechanism. So we're telling it to parse. We have to say what it is that we're after. We say we would like you to find an expression, which really means it should just launch this function on this input. And here's the input. And so now the parser comes back, and it comes back with the result. And now comes the unhappy part. So the result is this. So let's see what it has found. So it has found a 3 squiggle none. Why on earth a 3 squiggle none? The 3 came from here. And then it got up to this part here where it was looking for another star or slash, but there wasn't one because when you look at the input, there was a minus here. And so that one gave us a none. And probably at this point, you've lost all interest in this anyway, so I'm not going to talk about it any further. So by default, what the parser returns is not yet useful. So the parser, at the stage it is right now, will give a seemingly gibberish result when it successfully parses. If, on the other hand, you give it something that's not a valid expression, such as 3 minus minus 4, for example, then it would just fail. So right now, all it can do is distinguish correctly parsable stuff from that's not. What we really want is we want to return some kind of a value. So the first thing I want to try is let's make this thing into the world's most complicated pocket calculator and have it actually compute the answer. So what you then want to do is at each stage of the parsing process, you want to have the parse result transformed into the type that you're after. So in the case of a calculator, I want to return floating point numbers. So my target type is no longer any, but it is double. And I'm using double here because the division could give us doubles. Otherwise I could stick to int. So in the case of a number, I just convert it to double. The conversion thing is initiated by putting this hat operator there. Why hat? Because the precedence of Scala operators follows the traditional precedence that you have in C and Java, and hat is low on the list. So it binds much more weakly than others, and that turns out that it's convenient for putting it in those places. But it binds stronger than the or, which is also useful. So so they just used hat for this reason. So what you do is after each of these grammar rules, you put in the hat, and then you say what you actually want it to be to get. So in this case here, we say take the string A whole number returns a string. It returns the string that's been parsed. Take the string and turn it into a double. Now let's look at the case where we said that a term can be optionally followed by a plus or minus and an expression. Now what do I want to do? I want to get a parser of double, meaning the return type is, or the value type is now double. And I need to get a double that's composed out of whatever came out of the term, which by recursion is going to be a number. So this would be a scenario where I have, for example, 4 plus 5 times 6. This here would be a term. And ultimately, eventually, this would come out of by parsing this sub-expression. So this term here, through recursion, is already going to give me the number 4, not a string, but the actual number 4, because it too will return a double, and its parsing will have already completed and gotten me 4.0. So I'm now matching this 4. I'm matching it squiggled together with what? In this particular case, I'm getting a 4 squiggled together with a sum of a plus and another expression, which I call b for right now. And so I'm getting an object that looks like this. It's an object that's an instance of which class? This object here. It's an instance of which class? No. Squiggle. It's an instance of squiggle. It is made by squiggling together a 4 and that sum stuff. Okay, so I have an instance of squiggle, and I say, if I have an instance of squiggle, where on the left side I have something and then I have a sum, and then a plus and another squiggle b. In this case, what I want to happen when this thing is evaluated, I want to add a and b. So a has to already be a floating point because a comes from term, and term returns a parser of any, no, a parser of double, so its result is a double. So I have a double on the left, and how about this b here? How do I know that's a double? That I know because that comes from expr, and expr is also a parser of double, so it has to yield a double. So then I can simply add them, and the compiler knows all of this, so when I say a plus b, it's not surprised what plus means. It's the plus that adds two floating point numbers together. And of course then the same thing for the minus part. Then I have the minus squiggle b. Yes?
I have a question about pattern matching.
Yeah.
When I do math, I can put like a brace and do pattern matching with the case like to do with the hat.
Yes?
But if I have a function with only one parameter, I still have to use the match keyword. When do we use it or not? Because there's no match here.
That's right. So this is what's called a partial function, and there is a syntax that when a function is expected, you can give it this kind of thing. So the argument of hat is a function. Any old function that transforms whatever it is that the left-hand side delivers. This thing here delivers a string. This thing here delivers a squiggle of a double and a bunch of other squiggle stuff. So whatever this thing gets delivered then gets put into whatever function I put here. And so there is a shorthand notation for a function that hopefully you will be seeing the week after next that has just this form where you have a bunch of case statements. And so it does what you think it does. It matches the argument against this. So to use this library, you don't have to know the syntactical wrinkle. You can just approach it from the level of magic that says that after the squiggle, you're allowed to put in a bunch of case statements. And that's how I would do it when working to build a parser. So, so this rule here will kind of on the fly add together these two arguments or subtract together these two arguments. Now, as you can see, it's a little bit tedious when you do this, that all of this intermediate junk, the sums and the pluses, that they're all there, because really all we care about here is the a and the b so that we can add or subtract them. It is kind of necessary to have the plus or the minus, I guess, so that you can figure out which of the branches you get in. But sometimes you really only have junk. Let me give you the example here where you have the left parenthesis, the expression, and the right parenthesis. And of course, you could then now say hat case, left parenthesis, squiggle, E squiggle, right parenthesis, and then return E. But that's tedious. So they give us a nifty shortcut that if instead of using the squiggle operator, you use the squiggle arrow operator, the squiggle arrow will match just like squiggle, but it'll throw away the side that's not at the arrow. Yes?
Maybe that's why they didn't choose arrow.
Oh, they could have used an arrow with two. But yeah, I don't know. Oh, that's interesting. So in this case here, it'll throw away the left parentheses. It'll also throw away the right parentheses. And what's left over is just the expression, which is already a double, because all of these parsers return a parser of double. And then you don't have to transform it anymore. We wanted a double, we got a double, and we're good to go. So in this case here, we've now turned all of the parser of any into parser of doubles. And then when you run this thing, and you'll see that in the lab, it'll evaluate the expression through the kind of normal recursive descent evaluation of expressions. And when you look at the Scala code, it's really pretty simple. It just contains these three functions, expression, factor, and term. It rewrites the results, and that's the end of it. And it's all right in the Scala language. You don't have to, like when you use something like ANTLR, you have to write the grammar in a special language, which itself has a grammar. Then ANTLR reads it in, turns it into a program, and it's all much more ceremony than here. You write in Scala, you get a perfectly nice little parser by these few simple rules. Now, yes?
I think the idea behind this freedom is that it replaces just a space. Because if you take the grammar and then you can just copy paste the grammar,
Right.
and then you replace all the spaces by these characters. So it's not. I mean, arrow is something that is used usually for other types of semantics. And here the idea was just to copy paste your grammar and then just you replace whatever space is there, because a space is like sequence in a grammar when you write a grammar.
Well,
when you write A space B, it means sequence. So you just
Right.
have to replace every space by this character. That is
Well, the thing is, you need some symbol because you need to combine the things, right? You can't just use a space. So you need an operator.
yeah.
But there's no semantic, yeah,
replace the
yeah.
space,
But there's no semantic difference between a squiggle and a pair.
Yeah, no, I'm just
Right.
thinking in terms of the appearance.
Right.
You take a grammar, you copy things, and then you
Right,
replace
right.
it.
But the question was, why make a new operator as opposed to using an already existing operator? And actually, there was some reason. I can't remember what it is because, okay, I'll figure it out while you guys labor on the. But there was a genuine reason. It wasn't random or just because it's prettier. Yeah.
My bachelor's work, I'm doing a parser with ANTLR.
Uh-huh.
Should I drop it and do it in Scala and import Scala from the Java?
So it depends on what you want. That's a very good question. So the sweet spot for these parsers is if you need it done quickly. So they don't perform as well as the best parsers that you write with ANTLR. But so if performance is not an issue, but speed of development, then they win all the time. So what I would do is, yeah, I would absolutely write it in Scala. First get it to work, then get the rest of the program to work, and then if performance happens to be an issue, which it often isn't, then you can go and rewrite it in ANTLR. But for something quick and dirty, it's awfully hard to beat these combinator parsers. And the syntax here, once you get the hang of it, is quite nice. So when I teach we have a programming languages course, and so they used to do it in Scheme, and so I do it in a small subset of Scala. And when we do parsing, that's what we do. So we parse like a dozen little languages like that, and it's very easy to go from one language to the next. much less of a hassle than having to do the ANTler stuff. But what to me is the most amazing thing really is that how the features of the language collaborate so nicely to do what really is a very powerful library. Because like Nestran said, all you have to do is you take the grammar, you replace the spaces with squiggles and the stars with rep and the question marks with opt, and there you have your grammar. Or if you never knew what a grammar was because evil people have eliminated that course, then you can just say this is the syntax of the grammar, just with the vertical bars and the opts and the reps. So if you just want to do an expression evaluator, then what you've seen is good enough. But usually one parses because one wants to do something else, such as generate code. And in that case, you actually want to generate a tree that describes what it is that you have parsed. And then later one feeds the tree, say, to a code generator that walks the tree and attaches types, generates machine code or virtual machine code or whatever. So for this very simple case here, what do we have in our in our trees? We'll make a node for numbers, for variables. We're not actually going to be using variables for this very simple thing, but of course you would in a real programming language. We'll have things like for sums and products and differences. And so the way I've done it just here for simplicity is I've made a node sum, where the left is an expression and the right is an expression. So we're going to be making an expression tree out of this. So for example, when we see 3 minus 4 times 5, we want to get the difference of 3 and the product of 4 and 5. And that's, we could evaluate it, but really the idea is out of that we can generate machine code, if that's what we want. So that is just as easy as just doing the evaluation. All I have to do is where it used to be parser of double, I now say parser of expr. Notice that expr is the common superclass of all of these case class things. Expr itself isn't a case class. We'll never match expr against anything. It's an abstract class. In fact, I could write abstract here if I wanted to. And it would be a good idea to do so. So all of these are exprs, and the parser will return an expr, which is either a number or a variable or a sum or a difference or a product. So, and here where it used to say a plus b, now I return this sum of a comma b. That's the only change I need to make to my parser. Now it's become a, and of course for all the others, for the difference and for the number and so on. And now this parser will return these trees. So there is a small problem with the grammar here. So when you look at 3 minus 4 minus 5 and see how it's parsed, the way the grammar rules were is an expr is a term, then there's an optional minus expr, so that gets taken, and then that again becomes a term minus expr. And when you look at what tree it returns, for 3 minus 4 minus 5, it returns this tree. So the trouble is that there was an expr at the end, and then the tree is wrong, because if I now were to evaluate, it gets the wrong result. You know, if you have this thing here gives you 4 minus 5 is minus 1, then you get 3 minus minus 1, which is 4. But what you actually would like is you would like it to be, 3 minus 4 is minus 1, minus 5 is minus 6. So that's annoying. So, and that's because we want these operators like subtraction to be left associative. So there's a couple of remedies. We could say, who needs subtraction? And just stick with addition, which is commutative, and then it doesn't matter. But in practice, I guess we have to support subtraction, so we have to do something. Could we switch expr and term? So could I, if we go back to this rule here, could I call expr here and then term here? Now, from the abstract theory of grammars, there's nothing wrong with that. The grammar is still the same because the grammar is not something executable. But in our case, it is executable because these are actually functions. And now what will happen is that as soon as one calls expr, when it tries to match something, what's it going to do? It's going to call expr. It's just a function. It's going to call expr. It's going to call expr. It's going to be an infinitely recursive call. So in Scala, this simple approach doesn't work. It turns out one can make it work with something more complicated, but what we're going to do instead is we're going to change our parsing strategy. And so this is a general problem in parsing that you just sometimes have to change the way that you approach it to be able to parse something effectively. And so what we're going to be doing is when we have something of the form 3 minus 4 minus 5 or 3 plus 4 minus 5 plus 6 or something, we're going to be gathering all of those terms together and then turn them into the right tree. And so that's what you see here. We're going to take a rep means a repetition of any number of pluses or minuses followed by terms. And so notice that we now have a term and term. So all of these are terms. We push everything down a level. That way we avoid the recursion. And then we will manually group them left to right. And it's a little bit tedious to do that, unfortunately. So what you get is you get out of the parsing, you get like when you look at 3 minus 4 minus 5. Let's have a look. So you get this term and then a squiggle with the rep. The rep turns into a list. So it's the term squiggled by this list. Each of the elements in a list is a pair where the left is the operator and the right is the operand, already evaluated. So now we need to, out of that, compose something that's that has sums and differences in it. And so the way we will do that is we will iterate over this thing. We will then make a difference of 3 and 4, and out of that thing, then we'll take the difference of all of that and 5. And that turns out to be the right thing. So if I draw the parse tree that we want, oh, here it is. We want 3 minus 4, and out of that, we want the minus 5. So this is a picture that you may remember from when we did folding. You have an initial element here. You have a bunch of elements of the list, and you want to combine them in this way. So this is exactly the fold left scenario. So here's the code. We have this cumbersome expression that is a term followed by pluses and minuses in terms, and we want to fold it in with some operation. And what is the fold operation? When the thing that comes in from the fringe here, when it is a plus squiggle y, then we turn it into a sum. When it's a minus squiggle y, you turn it into a difference. When you do that, then you get a parser that gives the expression in the correct way. So that's a bit unfortunate that we have to do these things, but really it's not Scala that's to blame. It's our stupid notion of arithmetic, right? I mean, why do we have infix operators that are left associative? I mean, that's silly. We could have arranged that differently, but that's history. So a couple more examples that you'll need for one of the homework assignments. How would you parse something like this, like array bounds? In this case, that really is very simple. You would use rep so that you repeat something. Now here I've made, and this is a trick. Oops, a trick with a typo. I should have put a def here. In general, when you find that the grammar gets kind of complicated and hard to read, don't hesitate to put in new functions. So yes, a bounds is a rep of a bound, and a bound I define as the bracket, the whole number, and the bracket. Notice that here I'm using these squiggles with the arrow to get rid of the brackets. Once I've matched them, I don't want them anymore. And then the operation here is just a toInt. And so what this thing gives me is a list of int. Without further ceremony, this turns into a list of ints of the bounds. Now that's a simple repetition. Often you get a repetition with separators, like a comma here. And so here I have a function, it has an ID. It has a bunch of arguments. And to parse those, I need to use the rep. I could do it by hand, but it's easier to use this operator. Rep sep will automatically grab any number of things separated by whatever separator I want. Here I use a comma. And it'll match that and turn it into a list, throwing away all the separators. So when you do something like functions, you can do that as long as the separators are uniform. So that's all you need to do to parse something. So I will make you do two things. The first one is kind of mundane. I will make you just try this expression parser so that you can see it with your own hands and finish it up so that it actually generates these expressions. And then you'll see, you get a bunch of expressions out of it, and you can imagine that you could eventually turn this into a compiler if you added statements and loops and functions and all of that to that. And if you ever wanted to know that, you could look at the slides of my programming languages course to see how to do that over a semester's work. The other one that I'm going to show you is much more fun. So you've probably seen JSON at some point, the JavaScript object notation. When you do web programming, you make a call to some web service. More likely than not, in this day and age, you get the result back in JSON. So JSON has arrays. Oops, it has these hash tables, these name-value pairs, and integers and booleans. And it is so when you look at the JSON website, you will see the grammar for JSON. It's right here. You see them here in little railroad diagrams if you like to look at them like that. But it's a pretty simple grammar. And here is the grammar in Scala. So a value is either a string literal, a floating point number, an object, an array, true or false, or null. And then we have what's a number here, what's an object. An object is a squiggle followed by members. And a member is the string, the key for the object, the colon, and the value. And I'm going to let you figure out what the array is so that you get to do something. But it's totally easy to do this. It takes a few minutes to turn this into a grammar in Scala. And then when you parse it like this, it's going to give you a parser of any, of course, which is not really useful. And now in Scala, what do we want? We probably want, for an array, we want a Scala array. For a JavaScript object, we want to have a Scala map. That's the logical equivalent. And so that's exactly what one wants to do. And it's easy to do, and you'll see. It's just super, super easy to do. And you'll get, in less than 10 lines of code, you can parse JSON. Yes?
Don't you need a dot element? Because JSON files always are one object with starting.
Well, here we're going to say that we know what's on top. So you will either ask for an array or we'll ask. Yeah, but that would be better. Well, I can never remember. There's some ambiguity whether you can have an array on the top. Let's find out.
Grammar page, at the right in the, I think object is
You may be right.
After that, each JSON file is an object.
Is each JSON file an object?
yeah.
Okay. Okay. So then
The initial
fine.
object.
Yeah. Yeah. The parser itself is neutral on this question, right? When you actually parse, you have to say what it is that you want to parse. So when you want to put this to work, you say, I'm looking for an object. So what you're saying is this is actually a bad example. This is not a JSON object because it's an array. Yes.
But I think it helps a lot for students to actually go to this page and to take exactly the grammar as it is and just try to copy paste and this part, object members, that's.
Right, that would have helped, except I've already done it for them.
Yeah, I mean, for the array and the.
Yeah, yes, yeah, for the array, you know, by all means do it, yes. Yes, all right, let's get going with that, and
We already had a course in grammar, so we had enough.
what's that?
We already had a course in grammar last year, so.
The paradigm.
Oh, I see, okay, good.
Did you see also context-free grammar?
BNF, BNF.
LL parsers also? Left.
Yeah, I wasn't sure, so I dumbed it down.
That's
That's okay.